Our next speaker is Sergey Agapov from Sobolev Institute of Mathematics and the Novosibirsk State University. He will talk us about the construction of exact solutions in the problem of integrable geodesic flow. Please, you're welcome.
Dear colleagues, first of all, let me thank the organizers of this nice conference for possibility to participate and to give a talk here. So I'll be talking about integrable geodesic flows and also magnetic geodesic flows on two-dimensional surfaces. And before going into details and describing the main problem and the main aim of my talk, let me first of all briefly recall you some very basic definitions. So consider a two-dimensional surface M with the Riemannian metric. Given a metric, we may construct a Hamiltonian in such a way, and as well known, the corresponding Hamiltonian system describes the geodesic flow or the given metric. Also, I would like to recall the notion of first integral, namely an arbitrary function which f, which depends on coordinates and momenta, is called the first integral, or equivalently the conservation law of this Hamiltonian system if it conserves along the trajectories, or equivalently the Poisson bracket of f and the Hamiltonian vanishes identically. So, of course, one of the key property of such Hamiltonian systems is to be integrable. So, as we know, the Arnold-Liouville theorem says us about integrability, namely such Hamiltonian system is called completely integrable if it admits a complete set of first integrals, which are functionally independent almost everywhere. So in this case, Hamiltonian doesn't depend on time explicitly, so it of course conserves. It is the first integral itself. So for complete integrability, we need just one more first integral, f. And if the system is completely integrable, then the equations of motion can be integrated in quadratures. So at this moment, we arrive to one of the classical problem of differential geometry. Given a two-dimensional surface, we want to describe all the possible metrics on it with integrable geodesic flows. So in this case, this problem reduces to searching just one more function f, which conserves, and plenty of works is devoted to searching of such function. Many mathematicians investigated this problem in this way. So it seems to be, for me, to be the very natural way to investigate this problem, and I will follow this way as well. And as I shall demonstrate it a little bit later, searching for the first integral can be reduced to searching for solutions of certain quasi-linear system of PDEs of such form or maybe such form. It depends on coordinates which you work in. Here is U is a column of the unknown functions U1, UN, which depends on two variables, xt or xy. And matrices A and B depends on the unknown functions U, but do not depend on its derivatives. So we have such quasi-linear systems of PDEs, and they appear in many areas of mathematical physics, for example, as gas dynamics and many others. And
Excuse me, may I ask
Sure.
a question? The surface on which you see geodesic flow, is it just torus or the sphere? What about genus?
actually, one of the part of my talk will be devoted to two-dimensional torus, but at this moment we do not fix the genus. It doesn't matter at this moment.
So do you know any examples of integrable geodesic flows on higher genus?
In analytic case, no. There is a theorem by Valery Vasilievich Kozlov, and one of the main aims of my talk will be to describe systems of such a form which appears in the problem of geodesic flows and magnetic geodesic flow, and I also would like to describe some methods which sometimes allow to integrate these systems and construct explicit solutions to the system. Okay, in the overwhelming majority of known integrable cases, if a mechanical system admits first integrals, then these integrals are polynomial in momenta, or maybe functions of such polynomials. So it is very natural to start the investigation telling about polynomial integrals. And the first result I would like to tell you about was obtained by Valery Vasilievich Kozlov in 1995. So if we choose the conformal coordinates, then it states that for any number n, as large as you want, there always exists an analytic function such that its geodesic flow admits an irreducible first integral, which is polynomial in momenta of the given degree n with analytic coefficients, at least in a small neighborhood of a point. So in this sense, the family of integrable cases is pretty rich. And I would like to go into details a little bit and to tell us about the proof. The idea is very natural and quite simple. So if we consider a polynomial first integral of the given degree and write down the conditions on f to be an integral, then we obtain a certain quasi-linear system of PDEs of such a form. Actually, it doesn't matter which exact form it has. But the main idea here is that one may just apply the Cauchy-Kovalevskaya theorem to this system to prove the existence and uniqueness of an analytic solution. So that's the point. And as you can see, this is the existence theorem. And at this moment, a couple of very natural questions appear. And one of the questions is how to construct these solutions explicitly, how to integrate this system. And one more question is the following. What will happen if we try to extend these solutions from a small neighborhood of a point to the whole phase space? Can we manage to do this? And first of all, I would like to answer the second question. It concerns the behavior of the global behavior of solutions to such systems, and the main problem here is that in typical situation, if we, for example, choose an arbitrary matrices A and B, consider a Cauchy problem with certain initial data for the system, then almost always some derivatives at some points go to infinity and the solution blows up. This is a very typical phenomena, and I would like to illustrate this on this simplest case when we have just one quasi-linear equation. This is a very well-known Hopf equation, which also appears in many spheres. So we have this equation. We may consider the Cauchy problem for it, having the initial function, and a general solution can be given by this implicit formula, and it can be shown by the standard method of characteristics that if the initial solution is non-constant, then characteristics, in this case they are just straight lines, they intersect at some point and the solution blows up. It has a very clear physical meaning also, the initial profile G, and the higher any point is placed, the faster it is, and at a certain moment solution blows up. So this is a very typical situation for solutions to such quasi-linear systems. However, sometimes global analytical solutions exist, and I will show you a couple of them which relate to geodesic flows. One more obstacle to the global complete integrability was also found by Valery Vasilievich Kozlov in 1979. That is exactly what you were asking about, by the way. If we consider a surface of genus larger than 1, then on the surface there is no Riemannian metric with integrable geodesic flow, at least in the class of analytical functions. So these are certain topological obstacles.
And you said that was analytic, right?
Yes, of course. If we consider, for example, smooth, but smooth functions, then as far as I know, this is an open problem if this theorem holds true or not. Okay, now let me go to the first question I was asked about certain solutions which are known to exist. So if we consider two-dimensional sphere and two-dimensional torus, then there are many integrable cases. In the case of two-dimensional torus, these cases are rather simple. And the first example, which metric depends only on one variable, then a linear invariant of first integral exists. The second case corresponds to Liouville metrics, when one can separate the variables. In this case, the quadratic integral exists, and equations of motion can be integrated in quadratures in these cases. Okay, on two-sphere, there are also integrable cases, and there exist polynomial integrals of degrees 1, 2, 3, and 4. By the way, quadratic integrals on the two-sphere as well as on the two torus were described by Kolokoltsov in 1982. And what about integrals of degree 3 and 4? For example, if we consider equations of motion of a rigid body with a fixed point, then there exist many famous integrable cases by Euler, Lagrange, Cheplygin, Kovalevsky, etc. So in those cases, there exist polynomial integrals of degree 3 and 4, for example, and by Maupertuis principle, one may modify these examples to obtain integrable cases on the two-dimensional sphere. It was done in works by Bolsinov and Matveyev, and also Kozlov. And there is a conjecture about these examples on two-dimensional sphere and two-dimensional torus. This is all we know about it, and Kozlov proposed the conjecture that there are no other integrable cases which cannot be reduced to these ones. So this is the conjecture, and it seems to be true for two-dimensional sphere. I'm sorry, it seems to be true for two-dimensional torus, but it is still not proved, even in the simplest case for cubic first integrals, for example. So if we consider a cubic integral on two-dimensional torus, this problem can be reduced to these quasi-linear PDEs, and one have to search for solutions to the system. It doesn't look very complicated, but the only known solutions to the system which can live on the two torus correspond to this case when the linear integral exists and the cubic integral can be obtained by, for example, multiplying this integral on Hamiltonian, etc. So it's an open problem. There are many results on this direction which were obtained by Kozlov, for example, Denisova, and that's what I'm going to tell you about at the moment. They managed to prove this conjecture for two torus only under certain additional assumptions, either on the metric, as in the second theorem, metric is assumed to be a trigonometric polynomial, or these additional assumptions are on the first integral. So there are certain symmetries, either f is even on momenta or maybe even or odd in the corresponding momenta. Under these assumptions, they managed to prove then the integral of high degree can be reduced to an integral of degree 1 or 2. Another series of results was obtained in works by Bialy and Mironov. They didn't, they considered the general case, general metric, and general first integral polynomial in momenta. So they managed to prove that if geodesic flow admits a polynomial integral, then one may introduce globally semi-geodesic coordinates. F can be written in the following form. There are certain coefficients can be normalized in such a way, and this problem reduces to this quasi-linear system with such a matrix A. And one have to search for solutions to this system. Moreover, it turns out that this system has certain beautiful properties. It is semi-Hamiltonian. It means that, first of all, it can be written in the form of conservation laws. And one more property is that in the hyperbolic domain, it admits Riemannian invariance and can be diagonalized. So the now I would like to describe some methods which allows to integrate such systems, and let me start with the classical Cardograph method, which is very well known. So it deals with the quasi-linear system of such a form. We have two unknown functions, f and g, which depend on two variables, x and y, and ij is just functions of f and g. So the matter is that we just interchange the unknown functions f and g and the independent variables x and y. So we, after making some simple calculations, we obtain such a system of PDEs on unknown functions y, x and y, which depend on x and g. And in contrast with the initial system, this one is linear, and sometimes it is easier to deal with linear system. Of course, it can be generalized on the case of when we have more unknown functions. For example, extended Cardograph method deals with such a system, and to apply it, we need to construct an additional flow of such a form, and of course, these two flows must commute. And if if they does, then after similar calculations, we may obtain also a linear system on the unknown functions x, y, and t. Okay, and finally, the generalized Cardograph method, which was proposed by Sergey Agapov in 1985. It deals with so-called semi-Hamiltonian systems. So if it is already written in the form of in the diagonal form in Riemannian invariance, then first of all we have to construct a symmetry of the system, and then given this symmetry, we may construct a solution to initial system of PDEs, just solving the following system of algebraic equations. So the deal is that we, instead of solving these PDEs, we just have to solve these algebraic equations. And of course, sometimes it's not easy, and the only known example when this method works for geodesic flow. I also would like to say that if the semi-Hamiltonian system is written not in the diagonal form, then this method also works, and a slightly more complicated formula, but actually it doesn't matter at the moment. So the only known example when this method works for geodesic flow, it was described in the work by Abdikalikov and Mironov in 2019. They managed to construct an example of integrable geodesic flow on two-dimensional surface with a polynomial integral of the fourth degree. So the coefficients of this integral and metric were found explicitly by this method. Okay.
Is this on torus?
No way, no chance to construct it on the torus. They are of course not periodic coefficients. Just.
What surface is it?
No, I guess this is just a plane with maybe.
Oh yeah, it's local.
Yeah, sure. These solutions which are produced by Cardograph methods are almost always local, of course. Since we have to solve such algebraic equations, we have to inverse functions, just as in the usual Cardograph we inverse functions.
Can one see that it doesn't reduce to degree 1, for example? Is it something mysterious?
Degree 1, the matter that if a linear integral exists, then in some coordinates metric has the following form. It doesn't depend on.
You don't know what is the coordinates are, right? You could change a coordinate in this monster could simplify to something like.
Yes, theoretically it may be. Sometimes, usually you just maybe calculate the Gauss curvature, and if it is not vanishes, it doesn't vanish, then it's okay. But
maybe we calculate the degree differently. Anything that comes from Newton's theorem, like for metrics of revolutions and like that, is it degree 1?
yes, sure.
So Gauss curvature wouldn't vanish then.
Yeah, it's slightly different questions, but of course you're right. That's a right question, but this integral case seems to be non-trivial in that sense.
Yeah, it looks complicated enough, but who knows?
Yes, you are right. Of course. Okay, now let me go to the case of non-polynomial integrals, and the first example I would like to tell you about is the following. These two functions were found in this work, and these functions commute with respect to the standard Poisson bracket, and as you can see, it depends on the parameter alpha, which is arbitrary. So depending on this parameter, this integral can be polynomial, maybe rational, and even transcendental. And if we talk about geodesic flows, then it is enough to put f. Yes, here f is an arbitrary function of momenta. If we put f in such a way, then we obtain Hamiltonian which corresponds to a certain Riemannian metric, and its first integral is rational momenta. So from this moment I will be talking about rational integrals. And one more example. Excuse me, how much time do I have?
Still something, 10 minutes at least.
Oh, I think then I'll skip this example for brevity, since I'll maybe out of time. Okay, so the general result which was obtained by Valery Vasilievich Kozlov in 2014, corresponds to the case of rational integrals. And actually I started my talk by talking about analogous result by Kozlov concerning polynomial integrals of an arbitrary degree. And this is analogous result for rational integrals of such a form for any numbers, for any degrees of numerator and denominator. We always there exists such function lambda such that its geodesic flow admits such an integral. And also this is the theorem of existence. And in this paper Kozlov proposed a few questions. One of them was about explicit integration of the corresponding equations and searching for examples of such metrics and first integrals. So in this paper there were no examples. And this is what we were trying to do in 2020 together with Vlad Shubin. We considered the simplest case when the degrees of numerator and denominator are equal to 1. And in this case, the question of existence of such integral reduces to this PDEs, system of PDEs. And we managed to integrate the system and to construct a rich family of explicit solutions. And here in the slides are just some of these solutions. First example, there are Bessel functions, so non-elementary functions in metric and first integral. The other examples are expressed in terms of elementary functions. These two examples are trigonometric ones, and I also would like to notice that this and these examples are superintegrable. In these cases also exists a quadratic momenta first integral. And one more example when also in elementary functions. So I would like to maybe very briefly give you some key ideas of the proof, how I managed to construct this. But no, maybe if there is interesting, I may describe it after my talk. But at this moment, I will skip it, since I want to.
No, at least main result. What is the main result?
No, that's not the main result of my talk. It's just one of the results I would like to tell you about. Since I also would like to tell something about magnetic geodesic flows, for them there are many interesting integrable cases. So the last one thing I would like to tell about rational integrals, that very recently on Archive appears the work by Professor Kolodziński, who managed to construct certain examples of rational integrals, but from a completely different point of view. Okay, now I would like to tell about magnetic geodesic flow. In this case, we consider the Hamiltonian system, but the magnetic Poisson bracket has the following form. So momenta do not commute anymore, and this function just corresponds to the case of magnetic flow. And in this case, the problem is given a surface. We want to find such a pair of magnetic field and Riemannian metric, such that its magnetic geodesic flow is integrable. For brevity, I will describe only two-dimensional torus. So if there is no magnetic field, then, as already told before, these are integrable cases. And if there is a magnetic field, then these two known cases, two integrable cases are known when integrability takes place at all energy levels. In the first case, there is a Euclidean metric and a constant magnetic field, and there exists the first integral of such a form. And the second case, when magnetic field and metric depends only on one variable, in their case exists a linear in momenta first integral. So these are examples of integrability on all energy levels on two-dimensional torus. And yes, I think I'll skip it as well. I also would like to notice that integrability for the standard geodesic flow, it is just equivalent if we consider the integrability on a fixed energy level and on all energy levels due to homogeneity. So different energy levels have the same trajectories up to reparametrization. But it is not true for magnetic geodesic flow because dynamics changes on different energy levels. And the first result which can describe it in explicit form was obtained by Iskandar Alexandrovich Taimanov in 2016. He managed to prove that if we suppose that the magnetic geodesic flow on the two-dimensional torus admits a quadratic first integral on at least two different energy levels, then already in some coordinates, metric and magnetic field depends only on one variable, and in this case exists a linear first integral. So in this sense, quadratic integrals on two different energy levels reduce to a linear integrals on all energy levels. And after that, this result was generalized on the case of an arbitrary degree. If we have a cubic integral on two different energy levels, then the similar result was obtained in the work by Professor Butler and Naqvi. It's his student, she's his student. And recently, we, together with Alexander Valyuzhenich and later also with Vlad Shubin, we managed to generalize this result on the case of arbitrary degree first integral. This is written the idea of the proof. Okay, let me go further. And maybe the most interesting point here is to consider an integrability on the two torus on a fixed energy level. This question reduces to such quasi-linear system with such matrices A and B, and this system is also proved to be semi-Hamiltonian. And the main point here is that this system admits a rich family of global analytical solutions which live on the two-dimensional torus. And some of these solutions can be even written down in explicit form, and these solutions can be obtained from the work of these four authors. This is the initial system, and this is an explicit solution to the system. As you can see, S and R are elliptic functions, and all this construction is quite complicated, but it is parameterized by a certain number of arbitrary parameters, alpha, beta, gamma, etc. So this is the only explicit solution to the system which is known up to the moment. And also, it turns out that this system has an even richer family of solutions, and that's what we managed to prove in 2017 together with Bell and Mironov. But we cannot integrate the system and construct the solutions explicitly, so this is the existence theorem in some sense. And if I have some time still, I will give a sketch of the proof, because in my opinion it is very interesting. So of course this system has an obvious solution which corresponds to the Liouville metric and the zero magnetic field as for the standard geodesic flow. And then what we are doing, we construct a commuting flow of this system of such a form with such matrices A and B. So since this is a commuting flow, it transforms solutions of the initial system also into solutions. And we managed to prove that if we consider a Cauchy problem for this evolution equation with the initial data which corresponds to Liouville metric and zero magnetic field, then after transforming this initial data along this flow, we obtain something which is still a solution, but metric is no more Liouville, and moreover magnetic field appears. And this is exactly what is written here. So on the two torus there exist analytic Riemannian metrics with, which are arbitrarily close to Liouville metrics, and at the same time they are different from them, and also a non-zero magnetic fields, such that the corresponding magnetic geodesic flow admits a quadratic first integral on a fixed energy level. Okay? And
This is magnetic example, right?
sure, sure. Okay, so 1 minute, right? Okay, fine. The last one result, very briefly, together with my student Alexey Potashnikov, we managed to find the following integrable case. So this is still the same system which corresponds to magnetic geodetic flow on the two torus, but since it is semi-Hamiltonian, we decided to try to apply the generalized Cardograph method. So we construct certain symmetries of this system, and this method produces the following. So f and g are two unknown functions which satisfy the following two equations, and alpha, beta, etc. are just arbitrary parameters here, and the metric has the following form. And in the simplest case, when alpha and beta are equal to 0, we manage to find the explicit solutions, which is written on this slide. So, of course, this is not a two-dimensional torus, but nevertheless, certain explicit solutions are obtained. Okay, and that was all I would like to tell you about, so thank you for your attention.
Okay, thank you very much.